This is Dr. Frederick. We're just talking about the difference between a one-tailed test and a two-tailed test. And so what is a test? A test is a hypothesis test. We have a null hypothesis and an alternate hypothesis. And it's not easy for some students to see why this would be called a two-tailed test and why this would be called a one-tailed test. But that's what they are. A two-tailed test is one in which the null hypothesis concerns inequalities. Simply say the population mean, this mu, of one population is equal to the population mean of population 2, and the alternate says they're not the same. In a one-tailed test, there is an inequality in the null hypothesis. It says that the mean of population 1 is greater than or equal to the mean of population 2, and the research hypothesis is that mean 1 is less than mean 2. Most research hypotheses are in this form because generally when we go in to conduct a study, we have an idea of how things work. And so let's just say that this is a teaching method in which you have the old math and the new math, let's say, and you say that it doesn't matter which way that you teach, the mean of population 1 using old math, their mean on, say, a test, a state test, is going to be equal to the mean of the math test for students who get new math. Okay, and then the alternate hypothesis is that they're not the same, that one group will score higher than the other, and we can't predict which one will be higher. So you see, usually we have an idea which will be better. Now, why is this a two-tailed test? Well, we are going to form a sampling distribution. Well, I don't want to say sampling distribution. We're going to form a region in which we expect the difference of the means to fall if the populations are the same. You see, they'll be pretty close to 0. If the means are the same, they'll be pretty close to 0. And there'll be some variability from sampling if the means are the same. Now, these are not actual, like -1 scores. These are z-scores. But we're going to say that the means are going to be pretty close to each other in the samples if the means are equal in the populations. Oops. Okay. And where do we reject the null hypothesis? Well, if we have an extreme value on our test statistic, our t or z, if our t or z is way out here on either end, it doesn't matter which side it's on. If the difference mean 1 minus mean 2 is very highly positive, it'll be out here outside of this test region, and so it will fall past this boundary here, our critical value. Or if mean 2 is very much larger and mean 1 minus mean 2 is very small, negative, well, the value will fall out here. Either way, we reject the idea that they're the same, and we accept the alternate hypothesis. Okay. Well, there's two tails in which we will reject the null hypothesis. So this is a two-tailed test. Now, there's some times where we say, we believe that one method will be better than the other method, and then an alternate method, or I'm sorry, and so let me just start over here. There's times where we believe that we know which way things will work out. We have good evidence for that. So we say, look, the old math is not nearly as good as the new math, and we expect students who get taught by the old math will not do as well on the test as the new math. That's our research hypothesis. And because that's what we believe, we know how to form the null hypothesis, just whatever's left. Well, if they're equal, then we don't find this to be true. Or, if the old math is actually better than the new math, then our research hypothesis is also not correct. So, what we do here to set up our test region is to say there's only one situation in which we'll reject the null hypothesis, and that's when the mean for the old math is, when the mean for the new math is very much higher than the mean for the old math. So we're going to reject it when it's down here, okay? Because that would be consistent with our research hypothesis. So when it's very negative, we're going to reject that. We're only going to reject down in one tail down here. If mean 1, the old math, is much higher than mean 2, well, our research hypothesis was wrong, wasn't it? And so let's go back up here. Let me just fix this so that'll stop happening. Okay. If this is our two-tailed test, I want you to notice that the critical values where we decide to reject are at negative 1.96 here and 1.96. So we have to have a pretty strong difference between the means before we reject them. And what's the advantage of making our hypothesis in a one-tailed situation? Well, it's when I can, let me just fix this here. You see, we're going to operate at the 5% level. And let me just go back and do this again. Okay, 5% of the curve is in this white area. We split it. 2.5% is here, 2.5% is here for the two-tailed test. When we do the one-tailed test, we can put all the 5% down here on the bottom. And guess what? Our critical value is now much smaller, negative 1.645. So when the difference between the means is as little as negative 1.645, we reject the null hypothesis here, whereas we had to be really far out, negative 1.96 to 1.96, before we rejected the null hypothesis in the two-tailed test. So just to summarize, the two-tailed test is when you have an equality in the null hypothesis. You can reject the null hypothesis if your value is very low or very high. And a one-tailed test is for a directional hypothesis. And the advantage of the one-tailed test is that your critical value is much smaller. The 5% is all shifted to the left, which puts this value very much easier to beat than when you use the two-tailed test.